guys. I hope all of you have found the live stream yet again and are ready to start learning. How are you guys doing? Hello guys. I hope all of you are okay. Just checking, make sure it was streaming. So, please remember to check in on the form that's been pinned up to the top. You can also find that check-in in your module 1 in Teams. Please check in before 7 p.m. The form will close at 7 p.m. and you won't get your credit for doing so. So it's very important that you check in. Okay, so before we get started on formal lecture, I am going to take the time with a little bit more of Teams set up. I'm going to take the time to go ahead and walk you through what it looks like again. And then we will go from there. Now we're going to do Pomodoros, so I'm only going to spend 25 minutes on this, and then we'll take a 5-minute break where you can ask questions that you have. So, if we look at Microsoft Teams for you guys, and I am going to do a podcast that shows how this looks from at least an iPhone, and from an iPad, but I don't have an Android phone, so I can't show you how it looks from an Android phone. But if one of you has an Android phone and is willing to take screenshots and share those with me through Teams chat, then I will add that to the podcast. But I will be making that tomorrow. But anyway, this is what Teams looks like from a PC. And for you guys, I'm not going to worry about check-ins. It was not recorded. I have 0 responses. So make sure you hit submit on that. Make sure you're checking into the Lecture 2 check-in, which I'm going to show you how to access. But it should be the right form. Yes, that is the right form. Okay. Anyway. Back to Teams. Make sure that's okay. So, you want the 113.4 Teams. You won't see the 114.4 Teams because you're not there. That does not mean that you can't attend the 114.4 lectures if you for some reason wanted to do so. They are also public live streams. But I didn't figure you would want to do so. Now, the team is more set up. I haven't bothered with the home page yet. There is a shared calendar up here, and you can see that the lecture is in that calendar. And if you hit join meeting, it would send you to the live stream. Additional meetings will be posted in this calendar. Do not share this calendar in the chat. I had somebody in 114 that did that multiple times. The calendar is in the Teams. Everybody can access it there. Please do not share it in the chat. Now, these things, assigned announcements, those are where assignments that you will submit through Microsoft Teams will be posted. There are very few assignment announcements that you are going to submit through Microsoft Teams. Most of those are going to be in the quote bonus category. We'll talk about that in a minute. But very few assignments will be in there. The DNS assignments is do not submit assignments. I'm going to remind you again, I said this last time, but every single column for a grade, like exam 1 column, exam 2 column, any quiz columns, every single graded column has to have an assignment associated with it. Most of those assignments you don't have to do anything about. Just like today's check-in for this lecture. That's technically an assignment. You don't have to do anything other than check in. That's a form. It's actually not tied to an assignment here. I will tie that in to a weekly participation grade instead of having to do 28 check-ins. I'll do one a week. So much easier on me, so much easier on you. But that means that you're not submitting these. And they'll appear in this DNS assignment, and I don't even have that set to show up on your team, so you may not even see that. Interesting videos. That's where I'm going to post videos that you might be interested in watching, and some of those videos will have bonus assignments associated with them that will be in the assignment announcement. Question and answer. This is where there are multiple ways to get your question and answer points. Yes, you will be taking notes today. Because we will be lecturing today in 20 more minutes on chapter 1. One of the ways to deal that you're going to get points for question and answer are, of course, the questions you guys are asking in the live stream. Now, it's a little bit hard for me to recognize your names sometimes, so if you, for instance, don't see points and you know you asked a question in the live stream, you might want to chat me and tell me what your YouTube handle is. But other than that, that's one way. Another way is to ask questions in this questions and answer. And every Sunday, I will put a new announcement screen, and that'll restart, so there will be a week 2 Q&A and then a week 3 Q&A. So that's another place where you can ask questions. Now, let's talk about that in general. The best place for you to go and find everything is classwork. So if you look at classwork now, you're going to see, for instance, under general course information, there is an official course calendar, and that is the official calendar. That is the calendar I will be using to set up the graded assignments. There's the course assessments and grade scales. So if you click on that, it's a PDF. It shows you all of the points available, how that's going to be determined, different ways bonuses are going to be determined, total number of points, the maximum grade you can score, and the grade scale for the course. And also what university approved excuses are if you were missing an in-person class, i.e. an exam. So there's that. There's also the official course calendar. That's because you logged in using QMail. You cannot log in using QMail. You must log in using the same thing you log in using Brightspace. So I will remind everybody, you must log in to Teams using the same login you use for Brightspace. So first.last number at login.cuny.edu. This is why I told you to download the Teams app. Do not try to do this every time through the web browser. If you do that, you're going to have a problem with this every single time you do it. Because through the web browser, it's going to remember your QMail login, not your CUNY login. Download the Teams app and you won't have a problem because you will log into the Teams app once using that. And then you won't ever have a problem with this. Now, you may have a problem, for instance, seeing the whiteboard, and you're going to have to pay attention to how you're logged in up at the corner of your whiteboard to make sure you can see this. So if you can't access and see the lecture whiteboard for a given lecture, just check how you're logged in. But everything for Teams and pretty much any of the business things associated with Microsoft, you have to log in using your login.cuny.edu. Pretty much the only thing that you can access is your email through QMail in terms of the higher level Microsoft stuff. So always log into Teams using login.cuny.edu. This will be much easier if you do this through the app, because you'll only have to do it once. Okay, so in classwork, you will also see I uploaded the Chemistry Atoms First OpenStax book. That is the full book. And you will see that we now have an official course calendar. First page of the official course calendar just kind of explains stuff, and then it starts. So you can see week 2, we have an online meeting. You're supposed to check in. Sunday, there will be week 1 participation in questions. That's me. And there will be a bright space quiz. What will that quiz be on? Well, it'll be on the material we cover today and on the syllabus. So on this calendar, on the types of assignments you might get, and so on and so forth. So spend a little time going through teams and also on teams. So there'll be a little quiz, and then after that we have these, and I've put little check boxes where you can check off if you did this. This calendar is available for you to print. So you can check things and so on and so forth. It tells you where to submit stuff and so on and so forth. Now, notice these gray boxes. These are optional. If you have ADHD, one of the issues that comes with neurodivergence, also comes a little bit with autism, is the inability to start something. And if the something that you're supposed to be doing is really boring and you don't really want to do it, it can be exceptionally difficult to get yourself to do it. But one of the ways that you can be motivated is if somebody else is also just sitting there with you while you do it. And that's called body doubling. So on Tuesdays and Thursdays, I'm going to set up a YouTube live stream. I'm going to set some music that won't get me copyright struck. I'm going to put music on. I'm going to put a little screen on that does Pomodoros with my goals. And I'm going to sit here and do the stuff I'm supposed to do for you. Write solutions, write quizzes, and all of the things that go with maintaining and monitoring a class. And you guys can tune in and do your homework. And if you have questions, you can pop your questions up on live stream and I can answer your questions while you're working your homework. But I'm not going to be lecturing. I'm not going to be talking. I'm going to be doing my own thing. But at the end of each Pomodoro, I will ask you, did you meet your goal for your first Pomodoro? Did you meet your goal for your second Pomodoro? So it's just a way of having people be there for you and kind of hold you accountable for doing your homework while I'm holding myself accountable for doing my homework. So I've made that time available. It's also office hours. So you can just pop in if you have a question or pop a question during that time in Teams and I'll answer that question because that's part of this. So that's always optional, but it's there. So if you need help and you need body doubling and those times work for you, come on in and join and we will have a blast doing our homework. So those are there, bonus. So everything is here at this point. Everything's checked in. You have when it's due. You have when the exams are. Those exams will not move. The material on them may change slightly, but the exams themselves will not move. But that calendar is now up for you. And then as we go through modules, you'll now see, for instance, Lecture 2 is here. These are the chapters that we will cover in Module 1. Over the course of the rest of this week, I will begin to add reading suggestions of when you should read different things tied to that calendar. This is also where I'll post suggested homework problems. This is also where I will post all of the things like that. Now, I know if you ordered the Chemistry, a Guided Inquiry workbook from Amazon, it won't be to you until like February 19th. So the first few bonus assignments, I will be uploading to here. And then after February 19th, I won't be uploading workbook pages anymore. You will have to have the Chemistry A Guided Inquiry Part 1 workbook, because that's where your some of your homework will come from. In terms of the bonus, that's coming from Chemical Connections. Again, we talked about this, and it's available. The Chemical Connections, that's one way to get your bonus points. That's not the only way, but that's the way to be guaranteed to get 100 bonus points. Now, if you look at the course assessment and grade scale, you will see I listed several different ways to get bonus. So weekly Chemical Connections workbook activities, but you may not want to buy that workbook. Monday Chemistry Department seminars, that's another way. I don't know if we have 10, but that's another way. And then interesting videos and or readings. I can't guarantee that that's going to be 100 points. What I can guarantee is the weekly Chem Connection workbook activities are going to be 100 points. The rest of these, I can't guarantee if they're going to be 100 points. You may not can make the chemistry department seminar. But the point is there's multiple ways for you to get your 100 bonus points. Or to sum up 100 bonus points through a variety of techniques and ways of doing so. But that is on you. Once you get past 100 bonus points, it's capped. So, for instance, if you attended every department seminar and did all of the weekly Chem Connections, which will be graded, and you end up with, say, 150 bonus points, you get 100 of those. It is capped at 100. And you'll be able to see your bonus and how many points you have already earned, so that you know when you can kind of slack off and quit submitting bonuses. Now, there are a couple of other places where bonus is. Questions asked during the week, you can earn up to 28 additional bonus points there. That's not part of this 100-point cap. And there's also some bonus points in terms of the online quizzes. So again, that's not part of the 100-point cap. And occasionally I put some bonus questions on the exams, and that's just part of the exam score. So that's not part of the 100-point cap. So the 100-point cap is literally separate activities. Okay? And those will always be marked bonus, dash, and then a name. Any questions about that? So, everything will appear in this classwork and be guided. And in terms of the lectures, they will appear in this calendar. Now, one of the issues with calendars in terms of putting this calendar in terms of putting assignments, I think, if I remember correctly, is it kind of wants... it's kind of more set up for doing meetings than it is for set up to do assignments, and that's part of the reason why I created the printable official course calendar. So this thing you should print and put it in your notes and use it to check stuff off. I'm hoping I can create links to the Brightspace quizzes that I can then tie into this external links that I can link in, just like these whiteboards and stuff are linked in. We shall see. But hopefully we will do that. Are there any questions? Do remember, if you're shy about asking questions via the live chat, you can also ask questions in the question and answer portion of the main channel. That will pop up and I will see it. Or you can ask questions through the chat feature of Teams. Same thing. It'll pop up and I will see it. Um, you might not want to use the general, this goes out to everybody. This one, you might just want to ask me directly, but that's up to you. So, those are the multiple ways you can ask questions and get your question points. You post the questions either in this live chat or in question and answer. Just hit post in channel. This material goes through 11 chapters in a standard freshman chemistry book. So about 500 pages. We will cover about a chapter a week. So it's a lot. And if you're curious, it never slows down. So if you end up taking Gen Chem 2, we cover about 10 chapters, about a chapter a week. The material just gets harder. If you take Orgo 1, cover about 10 chapters, so about a chapter a week. The material just changes. So any other questions? Okay, so while we're doing questions, I'm going to flip us over to our break. This is the first of the Pomodoro breaks. At the end of this break, we will, I will answer questions during this break as they pop up. At the end of this 5-minute break, we will swap over and we'll start lecture on chapter 1. You can see in the classworks on the calendar, course calendar, it does tell you what topics we are covering on any given day. So you can see for today, Module 1, Chapter 1, Basic Chemical Literacy, Properties of Matter, States of Matter, Forms of Energy, Formulas and Models, and Units. So that's what we're hoping to hit today. Now I will tell you guys, because we covered this material in atoms first, there may be instances where you need some of the material from later in this course for your laboratory. I am going to try to make a series of videos that cover the pre-labs and how to do data analysis for the labs. But if you hit some of that material before I can hit the videos, please let me know and send me the lab experiments so I can do that for you guys. I still see 0 responses on the form. Well, let me double check. Let me refresh my forms. Okay, I have 27 responses on the lecture attendance forms. If you double submit it, you'll need to... If you haven't submitted your response, you've got 5 more minutes before it closes. Now this attendance will be there every time. When we are meeting in person, there will be an attendance sheet that'll get passed out in the first 30 minutes of class. Although I may just do it online and have you do it through your phone, since everybody has a phone for the most part. It's actually easier not to reduce paper, but one way or the other, we will take attendance. And the reason for that is, while I don't particularly care if you attend or not, what I can tell you is attending on time generally correlates with performance in the class. So students who, I suspect it's a false correlation. I suspect it's just that students who take this class seriously and treat it like a job, which is what it is, and hence show up on time every day that they can. Just they also do the homework and they study, so in general they do better in the course versus students that miss class or come in 30 minutes late or an hour late. This is a job. You should count college just like you count any job you've had. You should be on time. And one of the reasons for that is it has to do with respect. And if you want me to, or any of your professors to write you letters of recommendation, showing up on time and being present in the class and asking questions and interacting with the professor is the way to get a good letter. Showing up late or not interacting is a way for us to just tell you, I can't write a letter because I don't know who you are. So it has benefits to you guys, in other words. Okay. So I'm going to set my 25-minute Pomodoro timer. And let us talk about literacy. So when we are lecturing, when we start our journey in the sciences, we have a lot of vocabulary. And the problem with this is, in some classes, you have to memorize all of that vocabulary. Biology's famous as a course where you have a lot of memorization to do. In chemistry, especially in General Chemistry 1, there's a lot less memorization, or we say that, but the truth is maybe not as less as we think, because you do still have to know what words mean. And one of the real issues with science in general is just definitions of what a subject is can involve words that you don't know. So a good example is, what is chemistry? So if you look up a definition of chemistry, you'll see it's the study of matter. Sometimes you'll see it's the study of matter and energy. But what in the world is matter? Sometimes you'll see it as the study of matter and how matter transforms. That's even more complicated. So in other words, just trying to define what a subject is. What is mathematics? What is an algebra? I mean, you guys took algebra in high school. Did you know it has a formal definition? It does. And there are different types of algebras. You only did the type that involved numbers. There are types of algebras that involve vectors and matrices and three-dimensional spaces. So, but they're still algebras. So definitions give us a foundation that allows us to talk about the subject that we want to study. And that can be an issue when we say, oh, you don't need to memorize this. What we generally mean in college when we say you don't need to memorize this is it's not going to be like high school where we give you a matching for definitions. You know, here's a list of definitions, here's a list of words, match the word to the definition. So it's not really going to be like that. When there are instances like that, I will let you know. But these are certain things that you do need to know. So, atom. That comes from a Greek word, but it's basically the smallest. And even here, so for instance, the book that I've got says it's the smallest particle of an element. Well, now we have to define what an element is. That cannot be divided chemically or mechanically into smaller particles. Now, this definition has problems, real problems. The smallest particle of an element, that's okay. The issue is, and cannot be divided chemically, that's okay. The issue is, or mechanically, that's not okay. Because today we have high energy particle accelerators. Those high energy particle accelerators can collide atoms, and when you do, they get divided into smaller particles, which are called fundamental particles. So an atom is composed of other particles, but those particles are technically not something that you can play with chemically. So this part is something that I would not use today, because an atom can be divided into smaller particles. So, but we still have to define what an element is. So now, what's an element? And again, it's the same type thing. A pure substance, if we're going to be technical, we really should say neat, not pure. That cannot be divided be separated into simpler substances. Now, I'm a standard mathematician. I cannot spell. So, again, this is a really, this definition almost doesn't say much, and what it does say is not great. Pure, we tend to throw that word around, but it's problematic. Because when we talk about purity of something, we talk about, does it have, impurities. Neat indicates we have something that, to the best of our ability, is as 100% pure as possible. But that's okay. But cannot be separated into simpler substances, and yet we just defined atom as the smallest particle of an element that cannot be divided. So the element can be separated into atoms. So what do they mean into simpler substances? Isn't an atom a substance? So you can see why there's an issue with vocabulary when you start talking about chemistry. So here's how historically elements were defined. And I'm going to be sharing with you guys some videos that you can watch that really brings this to life more than I can bring it to life. Because historically, elements were defined by people would go out and condense air and then distill it. These are all chemical techniques, and they would get different errors. And that's what they called them, different errors. And then they would test those errors and see how they reacted. And if those errors reacted differently than other errors, then they knew they had a different substance. So elements were this stuff we cannot separate into something else in terms of reactivity. So elements were defined solely based on reactivity when they were originally discovered. Why? We didn't have a clue that elements were made of atoms. We didn't have a clue the atoms were made of other particles. What we knew is we have air, called ether at the time. We have this air, and if we condense it into a liquid and then let it re-expand as a gas at different temperatures, we get different airs, and those different airs have different properties, both physical properties and chemical properties. So I would probably define an element as a substance with distinct chemical and physical properties that cannot be separated into other elements. Now, that looks circular. I'm saying it cannot be separated into other elements. In other words, air, the air that we breathe, is a mixture of nitrogens, predominantly nitrogen, oxygen. It has a little argon in it, a little xenon in it, a little krypton in it. Has some CO2 in it, has some water in it. Right now, not a lot of water in it 'cause it's pretty dry, so the humidity is pretty low. That's what we breathe into our lungs. That's what we exhale from our lungs. That's air. Air is not an element, because if I collect air, and by the way, air does have chemical and physical properties, but when I collect air and then begin to warm it up, so if I cool air down and it forms liquid air, and I begin to warm that liquid air up, I get a new gas that comes off. I still have liquid, have gas up above it. That gas, if I collect that gas and form a liquid, that gas has very distinct properties. The first gas that we would collect as it comes off would be oxygen. Oxygen has very distinct properties. It's different from the properties of nitrogen, which would come off next. That's different from the properties of neon, which would come off next, then argon, then krypton, then xenon, then CO2, then water, in terms of as we warmed up. So each of these materials in air have different properties. But then if I just take that first gas that I collected, oxygen, we call it oxygen today, and I start trying to do the same thing, condense it to a liquid, then re-evaporate it, I don't get anything, nothing changes. It has the exact same chemical and physical properties it had before I did that. And that's because it's an element. It's a substance that's unique, has unique chemical and physical properties, and I can't get anything else. It's not a mixture. So that's kind of a better way to view it, even though it looks a little bit circular. But people for long have had issues defining what an atom is and what an element is in a way that doesn't lead to contradictions. So, today, we're lucky we're not starting in the 1800s when none of the elements were known. We have a full periodic table full of elements, so we kind of know what the elements are. Um, are there elements past the periodic table that we haven't discovered yet? Possibly. But since most of the elements on the lower half of the periodic table are completely unstable and you really can only find them for like a millisecond in a particle accelerator, I think for the stable elements we're good in terms of the discovery. But the history of how the elements were found and the periodic table was developed is rather an interesting history in its own right. And that's what some of the first videos that you can do for bonus will be about. Now, your book goes on to talk about the scientific method. Some of you that did science fairs, you had the scientific method shoved down your throat. The problem with the scientific method was it was always more of a guideline than a rigid thing. Now, depending upon the science you're working in determines how rigid the scientific method has to be. So as a chemist, I'm lucky. My scientific method does not have to be uber rigorous. In other words, I don't generally develop a hypothesis. I develop an idea or goal. Engineers have goals. I want to build X bridge across this from this bank to that bank. That's not a hypothesis. That's a goal. Most chemists don't have hypotheses. They have goals. I want to synthesize a compound that targets diabetes. I want to understand how electrons dissolve in supercritical fluids. That's one of mine. I want to understand how nanoparticles grow. That's another one of my research topics. That's not a hypothesis, that's a goal. And I'm going to design experiments to try to give me data to achieve that goal. But I wouldn't really call that a hypothesis. Now, if you're in biology and you're working on a model that requires an animal to tell you something, so you're going to modify the genetics of an animal and then you're going to test something on that genetically modified animal. It could be a yeast, it could be an animal, it could be a mouse, it could so on and so forth. There, you have to have a very specific hypothesis. Why? Because you are going to specifically genetically design something to allow you to test that idea. So just doing the genetic modification to get what you need to test the idea is a big deal. And you're going to have to go through institutional review boards because you're using live material, and they're going to have to make sure that you're treating that material humanely. And this is true, by the way, even if you're doing psychology, social science experiments, you're going to have hypotheses because you're going to be writing surveys and stuff based to test that hypothesis. And what's interesting about that is, if, for instance, if you go to the CUNY website on responsible conduct in research, i.e. research ethics, one of the biggest, baddest things you can do in terms of unethical research is what's called hypothesis swapping. In other words, changing your hypothesis. Now, that is a horrible thing to do. If you're halfway through an experimental study in social science, political science, biology with a live animal model, and you have specifically designed your survey or your experiments to test that hypothesis, and the data's coming back and it's not looking great, you cannot just change your hypothesis because your data doesn't match it. If you're an engineer or a chemist who has a goal, I want to understand this, your experiments change all of the time because generally they don't work the first time. I want to synthesize a drug that has this particular functional group to target diabetes. Your first synthesis didn't work, didn't put that functional group on what you were trying to do. So now you have to change the synthesis. Now you have to change this. Now you change that. Now you do this. When you finally make the stuff, now you test to see if it impacts diabetes. Now, that huge initial part, you were changing, quote, the hypothesis, the idea all of the time. But that's because you didn't really have a hypothesis, you had a goal. Now, the moment you say, okay, now I want to see, does it work for diabetes? Now you have a hypothesis. This drug will control diabetes. That's your hypothesis. Now you have to generate the biological testing to check that. Now it cannot change. So whether something's a goal or a hypothesis really has to do with the experiments you're doing, and do those experiments involve surveys or people or live animals? That's what determines whether you must have a hypothesis. And once you have a hypothesis, you cannot just change the experiments in the middle because your hypothesis isn't working. You have to follow it through to the end and look at the data. And then maybe reject the hypothesis and come up with a new one, or start again. Now, you could say we do that on the fly with goals. Okay, well, that experiment didn't work. Reject that hypothesis, try another experiment. But we don't really think about it that way when we're trying to just synthesize a molecule or understand something or derive a formula or something like that. So we're not truly thinking more formally in that type of scientific method. So it is you have to be incredibly careful with how the scientific method, how you, quote, apply it. Because different divisions of science either must hold to that method rigorously or don't use it really at all. I mean, we use parts of it. Well, yeah, since you don't really have a hypothesis, you can't really change it. You have a goal. So it would be like, I'm an engineer. I want to build a bridge from point A to point B. That's a goal. Now, first thing I'm going to have to do is decide what's the distance across from point A to point B. What's the best way, what type of foundations can I sink? What's going to be the best way to build that bridge? Does it need to be a suspension bridge or some other type of bridge? That's going to depend upon like geological surveys. Does it have to be earthquake proof? See, there's a whole bunch of stuff I got to ask to get from point A to point B. And I'm not even in the design stage of the bridge yet. Then design the bridge, then model the bridge, then test the bridge, and then eventually build the bridge. So the idea of the scientific method of test, analyze, establish, and go on, that's all there, but that's all, it's goal oriented rather than idea oriented, if that makes some sense. But that's a good question. So you do have to, hypotheses is such a formal term, and for a lot of the physical sciences, a lot of mathematics, a lot of computer science, and even some biology, it depends on what type of biology you're doing, you're not going to have such a formal thing. Well, it depends. And again, I see what you're asking. So say I want to make a particular compound, and I have an idea for how I can make that. So I run the experiment, and I test, I get something, I test it, it's not the compound I wanted. So I had you could say, okay, well, you had a hypothesis, this should make this compound, it's wrong, you reject it. And then you move on to what? The next, quote, experiment. But that, you would say, okay, well, but, that can happen in 30 minutes. You see, so was that really a hypothesis, or just I did an experiment and I didn't get what I wanted, so I changed the experiment? From my point of view, a hypothesis is much more formal. It's a long-term thing that you're trying to do, because you're going to establish a theory or a model. Um, when you're just trying to make a molecule, you're not really trying to establish a theory or a model. You're trying to make a molecule. Now, if you're an organic chemist, you may be actually trying to create a new synthetic pathway to make a class of molecules. Not just one, but an entire class that has a particular bonding structure. At that point, after a few experiments, you're going to begin to develop a hypothesis. If I mix this type of compound with this type of compound with this particular catalyst in this particular solvent, I get this type of bonding. Now you're beginning to develop a hypothesis, and now you can begin to test that and see how well does that hold, because now you are doing what? You're moving towards establishing a mechanism or a model for this type of new chemical reaction that's going to be broadly applicable across a very wide range. So you're not going to be just making one compound, but you're going to be making an entire class of compounds. So it just really depends upon what you're trying to establish. But generally speaking, in chemistry, you're going to do some experiments before you even try to do a hypothesis. And those experiments are going to be guided by a goal, not really a hypothesis. And in engineering, you're almost always driven by goals. So it's not, one of the fun things about science is it's not black and white. Okay, so we are at our next break. You can continue, during breaks you can continue to ask questions. This is just a break where you don't have to listen to me talk for 2 hours nonstop. Because when that happens, people just kind of tend to, I become Charlie Brown's teacher, wah, 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 wah. You guys quit listening, and no learning happens. So we're going to do our next 5-minute break. But go ahead and keep asking questions if you have them. It's not off topic about if you start an experiment and change your mind halfway through about what it is you initially want to do. That really depends upon, are you working with a goal, or are you really working with a hypothesis? In other words, are you working with animal models or protein models? I'll get to you, Alan, in just a minute. Are you working with animal models or even yeast models or fruit fly models? I have a biologist colleague that works with fruit flies. Or are you just working to create an organic compound? If you're working to create an organic compound, God, you change stuff all the way. Halfway through, you're like, okay, this is just not working. We're going to have to completely change how we approach this. Yes, you do it. You don't even bother to write a final report. You just trash what you did and you start. If you're doing math, if you're trying to do mathematics, math is really, really clean in this regard. You have, I want to prove this theory. You can spend 3 years, you can spend 15 years on, I want to prove this theory. And there's a lot of, well, that didn't work and you just shred it. I spent a year doing this, but it flat out is not going to prove this theory, and there's nothing in here useful to prove anything else, so I'm just going to shred it. Math can be really brutal in terms of research. So all of this really, really depends. But you cannot, if you're working with a mouse model or fish model or with human surveys, you can't not change the hypothesis in the final report. What you can do is say, we showed that this was a null hypothesis, and then you can use those data in future research. But you have to basically take your new hypothesis, get it approved through IRB, get permission to use those data to test your new hypothesis. It has to go back through review, institutional review, and then you can use those data to test your new hypotheses. This is really a pain in the butt if you're working with live animals or live anything, even if it's only partially alive. There is math involved. You have to be able to rearrange a mathematical equation. You have to be familiar with algebra. Not really trig. I hate trig too. But yes, you have to be comfortable working algebraically, without a doubt. But if you're not comfortable working algebraically, just pop me some questions and ask for podcasts that go over certain mathematical techniques that you feel a little bit hesitant about. And if you do that, you will find podcasts. That's why there is in the team that thing that says math review. As you guys ask for particular math, then I will make podcasts for those different math techniques. So don't hesitate to ask for what you need in that regard. Okay, so I was wondering if chemical indivisibility of atoms is a working hypothesis. Do we have experimental? We do have experiments that show that. And part of that is what nuclear chemistry is. So what happens in nuclear chemistry is you take an atom like uranium, and if you wait long enough, it transitions to a different element. And it changes its chemical and physical properties when it makes that transition. And it releases a ton of energy when it does it. So, but at the time that they were developing this idea, no, it was an assumption. It took hundreds of years to go from... You have to realize our understanding of science. I mean, these are wonderful questions. Our understanding of chemistry, or just that atoms are actual little atoms that we think about today, that comes from about 1890. So it's only been, 100 years, 200 years. Chem 2 requires logs, and there are some derivatives, but we tend to lean more toward deltas than derivatives. So you don't need a lot of calculus, pre-calculus for Chem 2. But, calculus is built on algebra, so... You don't really need calculus until you get to physical chemistry, but Chem 2 is basically an introduction to physical chemistry, but at the level where you don't need full-blown calculus. But good question. Okay, so one of the things that happens in when we start working problems in chemistry is you're going to find chemical problems are really, really, really wordy. They have a lot of words. And in the end, you're going to need to be able to read word problems. So this is where I do find that students have a problem. So most of you, for instance, can solve 3x equals 9. What is x? But if I say property A is 3 times larger than property B, and property A is 9 centimeters, how large is property B? Those two are the same problem. Property A is 3 times larger than property B. So A is 3 times larger than B. And then A is 9 centimeters. So 3B equals 9 centimeters. See, leads to the exact same equation, but it's words, not a math problem. This, from what I can tell, you very rarely work word problems in high school because most students really struggle with the fact that we're just doing basic algebra, but it's all in words. So, one of the suggestions that your book makes is to do a particular type of problem solving technique called COAST. So C is collect, O is organize. So collect data. So go through the problem and collect all of the data you have about the problem. And then organize the data into what you have, what you need, and what you want. What you have is what what the problem gives you. What you need may be certain conversion factors, certain values that you're going to look up in tables, and things that you have to look up. What you want is what's the answer that the problem is asking for. So in this case, the answer is how large is what I want. So what I want for this problem up here is how large is property B. That's what I want. What I have is, I have to get used to not having a scroll. What I have is that property A is 9 centimeters, and also that property A is 3 times larger than property B. Those are the two things that I have, i.e. this and this. And then what I needed, which is where the algebra comes in since you were asking, what I need is this relationship. which I developed from the two things that I have. Now, that developing from the two things that you have is where the A is. This is analyze. Analyze what you have, what you need, to figure out what you need. Take what you have and then look up what you need. Get that. Now you have that as well. And now you're ready to solve. So now I can solve this and get B equals 3 centimeters. And then the final thing is something that a lot of times students don't do. Think about the answer. Does that answer make sense? So, for instance, if you get an answer and you're like, well, that seems awful large based on what I had, or awful small based on what I had, then maybe you input something wrong in your calculator. Go back and check it again. Or, man, my units sure aren't the units I was expecting to get for this problem. Go back and check it. You've probably made a mistake. That's what think about the answer is. Don't blindly accept an answer because you think you got it right. Check. Double check. And this, by the way, this is why some people would argue, why do I have to take this course anymore? I mean, ChatGPT and AI can do all of these freshman chemistry problems. For the most part, it can. Every once in a while, though, boy, man, it makes up something. It does some really strange math because it knows kind of what answer it's supposed to get, but it can't figure out how to get it from the data that you gave it. So it just makes data up instead of looking up other, collecting what you need. It just makes up numbers and shoves it in there. So it should be around this. And you're like, no, that's not right. So that's the reason why think about your answer. And that's also part of the reason why we are still requiring you to work these type problems without AI. In a crunch, when your computer is down, say you're in Nashville right now, you are a nurse or a doctor in Nashville right now. There's no electricity across the entire city. They had an ice storm. Now, that doesn't, the hospital has generators. So you've got, your basic instruments. But there's no internet. So there's no access to AI. And there may not be cell phones because ice tends to take down cell phone towers too. So it's a lot like for those of you that lived through Hurricane Sandy, think about it like that. So those doctors, those nurses have to be comfortable in being able to do chemical calculations to work out drugs and concentrations of drugs and make IVs and all of the other stuff that has to be done when you're treating patients without the benefit of a computer to check them. If you're a nurse making rounds, you're going to have to check a doctor's dosage and calculations before you give it to the patient, and you're not going to have time to go check at a computer. So, how are doctors and nurses using AI then? Doctors are using AI for looking for small cancer in MRI imaging. It's very good for that. It's very accurate. It can see something that a doctor may miss because, there's a lot of complexity in MRI images or PET images. My mom's oncologist, he uses AI as a way of taking notes. So instead of having a scribe with him, another person in the room, he has his cell phone that he sets on and records the interaction he has with my mom. And then that gets translated into a transcript that he then checks, because he then has they probably have a scribe for that that hospital that then checks the accuracy of the transcript to the recording. But it means that he can be focused on her instead of focused on a computer typing notes while he's trying to talk to her. So it gives a much more personal interaction between the person, because he's not having to worry about keeping accurate notes. He's got it recorded on his cell phone. AI is going to generate a transcript of that, and it's an AI that's got all of the HIPAA regulations and stuff like that. Oh, absolutely. I mean, it without a doubt, critical thinking and all of that. But what I'm trying to give you, and it does reduce brain activity, absolutely. But what I'm trying to give you is more valid reasons, because I promise you, in a crunch, when you are stressed and you've got like 50 homework problems that you really need to work and you don't want to do it, AI is going to be really tempting. Okay? I understand that. What I'm trying to do is motivate you for why you don't want to use it, why you want to sit down and do that. And that's part of the reason why I'm willing to do the body doubling as well. So this is ironically, this COAST idea of problem solving for freshman chemistry is actually a little bit better than the scientific method is for how research is done. This pretty much is the way that everybody approaches problem solving in science. You collect data, you organize the data, and this is in general how we approach research in science. We collect data, we organize the data. What data do we have? What data do we need? What do we want? That organizing of data is where you either are generating a hypothesis or you have a goal. Because every hypothesis that you're going to have is going to be based on some preliminary data that you have collected. And what you need is, okay, I want to test this idea that I have. This is what I would need. This is the additional data I would need in order to test that. And the hypothesis or the goal is that's what I want. So COAST works even in terms of, it's kind of a more general scientific method. Okay. So I'm going to kind of use colors to divide as we move sections. But, and I'm going to try to remember to always use purple when I'm answering a question that you guys ask on paper, so that you can tell that on the whiteboard. Okay. So, now, I was just laughing at something that I'm about to talk to you about. When we begin to discuss elements and so forth, and I said chemistry was the study of matter, okay, what's matter? Again, here we go with these. Matter has mass and occupies space. Now this actually is a good definition of matter. This definition of matter avoids a problem that other books, I like this definition of matter from the Gilbert textbook. Most books has mass and volume. And the problem with the has mass and volume is an electron, which is a fundamental particle, and elements have electrons. Electrons have mass but no volume. But they do occupy space. So has mass and occupies space actually does account for electrons. So this is a very, very nice definition of matter. It avoids some of the issues that you can have. And then with this definition of matter, you can now define chemistry. They do a pretty good job of that as the study of the composition, structure, and properties of matter. That's a pretty good definition of chemistry. Yep, anything that takes up space. It works. Mm-hmm. Just because something occupies space doesn't necessarily mean it has volume. So an electron can occupy space because it's moving constantly. An electron never quits moving. So because it's moving all of the time, it occupies space. But it itself is a point particle, so it has no volume, but it does occupy space. Electrons are very, very confusing. So just so you know. Now, when we start trying to study composition, structure, and properties of matter, we tend to divide our studies, these properties, into two. We have chemical properties and we have physical properties. So physical properties, this is properties of matter that can be observed or measured without changing the substance into another substance. I'm going to give you a good example of this. I take ice, I apply heat, and I get liquid water. If I continue to apply heat, I get water vapor. Did I change the water? Did I change the inside that water? Did I change it into a different chemical when I applied heat? In other words, is ice and liquid water the same chemical? But it is. And that's and that's why I asked that way, because it is a fundamental confusion that we have about the structure. It is the same chemical. Ice is H2O that's just I'm online. It is at a different temperature, but it's the same chemical. And that leads us to chemical properties. So let me go ahead and define that. Defined by bonding. So, ice, in terms of the bonding of elements, is that. Liquid is that. Water vapor is this, in terms of the bonding. What's different is how close that is to others of its kind. So, what's different here is something called the density. And density is, from a fundamental definition, the number of particles per volume. Ice, water, and water vapor are all H2O. Ice, liquid water, water vapor, it's all H2O. The difference is the density. So, the density, the number, and this is something you guys wouldn't know because you're used to looking at density. I've got it as number of particles per volume. The other name for this type of density, as a general rule, just means per volume. So if you're in physics, there's energy density and flux density and all sorts of densities. Flux density is the number of magnetic field lines per volume. Energy density is the number of energy lines per volume. So density just kind of means per volume. So if I talk about the number of particles per volume, it is called number density. And we usually symbolize this as rho. The density we are more commonly using in freshman chemistry is mass density. And this is the mass of particles per volume of particles. And that is really important because we're going to later on have concentration, and concentration is going to look very similar. It's going to be mass of something per volume. What's different is what the volume is. In concentration, it's mass of something per volume of solution. Here, it's mass of particles per volume of particles. So, for example, where is it? This is a little piece of glass. It's the holder for my glass fountain pen that I use when I'm writing notes. This little piece of glass has a volume. I don't know what it is, but it has a volume. And if I weigh it, I would know its mass. And then I could define the density of this piece of glass as the mass of this piece of glass divided by the volume of this piece of glass. Now, this piece of glass is made of silicon oxide and probably some other stuff. And I could talk about, how much silicon oxide is in this volume of glass. That would be the concentration of silicon oxide in this glass. So they're very different things, density and concentration. Another good example of that is my nice stainless steel coffee cup here, or teacup. This steel teacup that I'm holding is made of a particular alloy of steel. Steel is mostly iron, but it also has carbon if it's stainless steel, and I think this one is. It has carbon, it has a little bit of chromium, it has a little bit of nickel. The chromium is what makes it stainless. So it's a mixture. It's not pure iron. I could talk about the density of this cup. I'd have to know the volume of steel in this cup, and then I would weigh it, and that would give me the mass, and then I would take the mass and divide it by the volume of steel in this cup. Not the volume of the cup, but the volume of steel in it. And that would give me the density of the steel alloy, and that would allow me to determine what alloy of steel my coffee cup is made out of. But then I could also talk about, for this same coffee cup, and the alloy would tell me what's the concentration of carbon in this particular alloy of steel. And that would be what mass of carbon per volume of steel I have. So they're very different units, but they have roughly the same units, mass per volume. So you have to be exceptionally careful to pay attention to not just the first part of the unit, but also the second part of the unit. If it's mass of A per volume of A, so I'm going to simplify this so that you can see. So if it's mass of A per volume of A, then it's a mass density. If it is, do not confuse that with mass of A per volume of B. This is a concentration unit. That's telling me how much A is in B. So be very careful with that. It's a common mistake that's made when we get later into the semester. Okay, so let's look at the difference between solid water hopefully I still have this. I do. Okay. Don't mind me, I'm trying to capture a screen capture something for you guys. There we go. Okay, so let's look at that. So these are pictures of what solid water, so what ice, liquid, and gas and water vapor. Now notice that the volume of the box is the same. So here, my density is 1, 2, 3, 4, 5, 6. So 6 water molecules per volume. Here I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 33, 1, 32, 33, 34, 35, 36, 37, 38. Here I have 38 water molecules per volume. And on this one, I have, and I'm going to count them if they're just right on the edge. 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 65 water molecules per volume. So, the density is different for ice, liquid, and vapor. What's the other thing you notice about these three pictures? Is there something else that you guys notice about these three pictures? Look at how the water molecules are oriented. What's unique about ice in comparison to both liquid and the vapor? Anybody? That's it. Ice has a pattern. And that's what makes it a solid. So, very good. Vapor or gas and liquid are also colloquially known as fluids. So if you were to later on go on to be engineers, and you might study fluid mechanics or fluid flow, that fluids are defined by random motion. Both the liquid and the vapor are moving. Yeah, liquid water is more dense than ice. That's why it floats. That's why ice floats on the top of your cold drink. So fluids are defined by random motion. And both gases and liquids are fluids. The difference is the density. And yes, what you said, the liquid is colliding. Ice never touches, and they don't, and that is kind of true. And ice doesn't touch because they don't move. So solids are defined by a rigid lattice. And that's really is the difference. A solid is a rigid lattice. And that technically means we can identify each water molecule based on where it's at in the lattice. In other words, I can call this water molecule 1, that one 2, that one 3. And that's going to be 1 all of the time. If I wait an hour and come back and look at my ice, That's still that molecule of water is still molecule 1. It didn't move. Over here, if I define this as molecule 1, if I come back in an hour, the likelihood that that molecule 1 is still in this spot is zilch. It's gone off somewhere else. So when I'm looking at water vapor, I have to kind of define and say, okay, in this volume, I have a water molecule. It's not, and then at a certain later time, I have another water molecule. It's not going to be the same water molecule. Can't guarantee it's the same. That's called indistinguishable. Same happens for liquid water. If I try to tag one of these water molecules and look at how it moves over time, what I'm going to find is it moves in and out and moves around the volume. Now, because the molecules are more densely packed in the liquid, where this particular molecule moves to is going to be in a much smaller random motion in this volume. Why? Because it keeps running into stuff. So it's kind of like trying to walk through a subway car during peak rush hour versus walking through a subway car not during peak rush hour. Not during peak rush hour, you can walk right on through a subway car. No big deal. You can walk from the front of the train to the end of the train. During peak rush hour, you're not going to be able to do that. You're probably kind of stuck in one train car because there's just too many people and it's not worth the effort. It would take too much energy to knock people out of the way to move to another train car. And that's in New York City subway. If you were a Japanese subway, you wouldn't be able to move at all. That you'd be more like ice because they pack you into the subway car. They literally have packers that shove people into the car. So there you'd be more like a solid. You're not moving at all. So these are physical properties of water. Why? In all of these instances, I'm not changing the chemical structure. It's still a hydrogen bonded to an oxygen bonded to hydrogen. What I'm changing is how these individual water molecules interact. See, for this water molecule, I'm going to tag a water molecule. There it is. Now, how far does it have to move before it interacts with another water molecule? There you go. That's kind of the interaction sphere. Here, how far does this water molecule have to move to interact with another water molecule? That. Here, this water molecule, the interaction is a constant. You see? So, what defines gas, liquid, and solid is density, and later on, I missed the final Pomodoro, but so what defines, this is an important concept though, what defines the difference between these phases, gas, liquid, and solid, is density. So density low. Now, it's not always the case that the liquid has a higher density than the solid. In fact, that's rare. Usually the solid has a higher density. So this density high, density high, random motion, random motion, fixed, so no motion. Now, what this means in terms of energy and interaction is, generally speaking, there are three types of ways things can exchange energy. What we're going to learn is the energy of the universe is constant, but we're not talking about the universe. So for right now, we can have kinetic energy, This is the energy of motion. We can have potential energy. This is the energy of interaction. And we can have heat. And this is, I'm going to call it dissipative energy or friction, because you guys have kind of have a concept of friction, so we'll call it that. Now, of these three phases, which one do you think has the highest kinetic energy, the highest energy of motion? That's correct. Gases have very high kinetic energy, very low potential energy. Heat, we're going to ignore right now, okay? Which is kind of standard in most of science. Solids have zero kinetic energy, and they have a potential energy that is constant. And that's because that interaction, there are no changes in the interactions. The solid is fixed in space, so there's no motion, there's no kinetic energy. There is a little bit, but that's really complicated and we'll get to it later. For right now, in terms of the gas, it has no kinetic energy. So relative to the gas, the kinetic energy is zero. So it's close to zero. And the potential energy is fixed. It's a constant, and that's because the molecules are fixed at a certain distance from each other. So the way they interact is fixed because they're not moving. Liquids have kind of medium. Liquids kind of have a kinetic energy and a potential energy that are similar. And that's a real problem. Of all of the phases of compounds, when we try to model them theoretically, liquids are the ones that we have the hardest time modeling. Solids are easy to model because they're fixed in place. So the kinetic energy is zero, potential energy is a constant, really easy to deal with. Gases are easy to model because while they do interact with each other, it's very rare because they're spread far apart, and every once in a while, because they're running around in random motion, they run into each other, and you have a brief instance of interaction, and then they're wandering off in the void again. But liquids are constantly interacting with each other. So they have kinetic energy, and it's a valid kinetic energy. They are in random motion. But they also have really high potential energy. And that potential energy is hard to model because of the random motion. So liquids are very, very difficult to model theoretically. And that's really ironic because almost all chemistry occurs in a liquid. When we start doing chemical reactions, it's going to be in a liquid. So it's kind of an issue. Because if we want to model our chemical reaction, especially if it turns out it's solvent sensitive, we can't model the solvent because it's a liquid. So this is the perpetual problem with chemistry. Okay, we're at a good stopping place. Next lecture, in terms of reading, what you should read, let me show you where we're at. So, we are in chemical literacy. We are in Essential Ideas. Now I'm using a different book, but this book relatively follows. So we just covered Chemistry in Context, section 1.1. Phases and classification of matter. That's what we've been talking about. So solid, liquid, gas. And we've kind of talked about elements. I haven't quite defined compounds versus molecules and mixtures. We'll get to that next time. But we've talked about it a little bit. We've hinted at it. And we've talked about atoms and elements at this level. And we've been talking about physical and chemical properties. So that's what we've covered today. For next time, if you want to get ahead on reading, which I will be giving you a reading thing so that you can stay ahead and read before lecture going forward, so on Monday, we will be covering measurements and error. So measurements, what's the difference between a measurement and a number, and what are units, and what are the standard units, and how to convert between units, and also what's error. So what's uncertainty, accuracy, and precision. That's what we will do next time. And then, in part of that will be significant figures. And then we will be through with this chapter. So, we will probably finish chapter 1 on Monday and move on to the next chapter. So, that's where we're at, and that's the one that we're in, Essential Ideas. Are there any questions before we end the broadcast tonight? If you have any additional questions after you go back and read and think about it, you can go to the question and answer area of Teams and just see post in channel. Just click on that, put a subject, type your question. That's how you do that. You could reply to it here, but you don't have to. I would just post. And I'll try to remember to check once a day and answer your questions in the questions and answer. If you don't get an answer to your question, chat me in Teams and ask, I put a question in the Q&A, could you answer it, please? And I'll do so. I have the attention span of a 3-year-old sometimes, so sometimes you have to kind of grab me and go, hey. Now, we will not do, I don't think I have it set up. The textbook in Teams is under General Course Information. That's the OpenStax textbook. If you're talking about the module books, you can go back and watch lecture 1 where I showed you the websites where you could get those. But I will post in here. The required workbook is Chemistry, a Guided Inquiry, Part 1. The optional bonus workbook is Chem Connections, and both of those you can find on the Queens College website, but I will remember to try to put them in general as well. So thank you, Zach. Ignore the snarky. It's 8:20. I'm a little bit off, but thank you for reminding me, and I will post links to websites where you can get them cheaper in the general channel. Now, Zachary, I don't know if you were here last lecture, but In terms of required textbook, actual textbook, I don't have one. OpenStax is free. You can go and download it, and that's why I posted the PDFs of that. But a lot of students don't find it very readable. So there are several other textbooks that you can easily get and use that are probably easier to read and understand. I just don't have a required one because I don't mind if you get an older edition of those textbooks for like $3 or $5. So if you don't find the OpenStax book readable, if you find yourself struggling to read that textbook, then there are some better books and you can pick one. But thank you for reminding me. I will go ahead and set this in general, post in channel, required books. I'll put links and get those posted. So thank you very much for reminding me to do that. Other questions? Okay, then. I'm going to end this broadcast. I shall see you. Have a good evening. It's common, but have a good evening. The textbook information will also be on a sheet, but I'm going to post links right now. So thank you for reminding me to do that, because I would have forgotten.